Uh, we know that time varying signal that is periodic, we would want with say certain period, time period t, it has a frequency f which is 1 over t, the angular frequency omega is going to be 2 pi f, then such a signal can be written as v of t is vp cosine omega t. In general can be written of this form, and this is varying with time, and Vp is called as the peak voltage, which is the maximum voltage value that the voltage will take, for example as shown here, the V peak. Sometimes what is useful is also to be defined as V peak to peak. This guy is the peak to peak, which is twice the peak. What you see here is the V peak to peak, which is twice Vp. So Vpp is going to be 2 times V peak. But what is also interesting to define for such an AC voltage signal, is that what we call as the VRMS, the root mean square. RMS stands for root mean squared voltage. And what that exactly means is that RMS voltage of that AC signal is that equivalent DC voltage that would dissipate the same power as that original AC voltage when it is connected across a resistor. Now let's see what that means by that. Let's say a simple circuit where you have a voltage source that is just simply directly connected across a resistor R. And this voltage source, though we write it as time dependent, being a DC supply, is going to be having a certain voltage V. Now based on that, we know that this current by Ohm's law that flows onto the resistor is going to be simply, the I of t is going to be simply the voltage over the resistor. So if we were to look at how this is going to look at in time, we see that this is a constant DC supply, so the voltage is simply one value, it does not change with time, and that is V. And maybe the current is going to be V over R, and that doesn't change with time as well, that is constant with time as well, and that is going to be simply V over R, and the amount of current that flows depends on this resistance R. Now if we were to define the power that is being dissipated by the resistor, that power that is dissipated, the instantaneous power is going to be simply V of t times I of t, simply V of t times I of t, and that is going to be the power that is going to be dissipated by the resistor, and that for this particular scenario is going to be simply V square over R. So for a DC, the power dissipated is going to be simply V square over R. Maybe to be more explicit, we call that VDC. VDC, where VDC is the DC voltage supply. Now we want to have an equivalent representation of this situation for an AC signal. Let's see what happens when you connect an AC source across this resistor, and this V of t, for example, can be of this form, having Vp cosine omega t. And if we were to look at how the time domain signal is going to look like, it's going to maybe cosine omega t, it's going to start on from Vp and all the way going to negative Vp. The V of t is clearly changing with time, but how about the current that flows through it, I of t? At any instant time t, at any time instant, the current I of t is going to be V of t over R by Ohm's law. So perhaps if you want to sketch it on the same graph, maybe the current I of t looks like this. This value over here is going to be simply Vp, the peak voltage over the resistance R, and that is going to be the maximum value of the current. Now if I were to find what is the power dissipated by this resistor, this is going to be I of t times V of t, no difference. The instantaneous power is going to be simply V of t times I of t. V times I, voltage times current, is the power. And whenever both voltages and currents are positive, I'm going to get a positive value. It goes to 0 somewhere here. And when both of them are negative, negative times negative becomes positive again, and I would get something higher as well, positive as well. But what you notice, unlike the DC case where the power dissipated is constant, here the power dissipated is fluctuating with time. With time it's fluctuating. So if we were to take the average power that is dissipated, the average power that is dissipated by the resistor, which by the way we just figure it out as 1 over T, because this has a certain time period, this has a certain time period, and that time period we want to average the instantaneous power across the time period. So essentially we need to find this integral, the area below this curve over the total time period, the area below this curve over the total time period, which is this range. This is going to be one full cycle, and that would turn out to be, in this case, since v of t is of the form vp cosine omega t, then I of t is going to be vp over r cosine omega t. So my v of t times I of t is going to be simply 1 over time vp squared over r and integral 0 to t cosine squared omega t dt. And if you were to go ahead and do that integral, you would notice that this would reduce to vp square over 2r. So in case of an AC, we get the average power dissipated is vp square over 2r, and for a DC it is v square dc over r. This factor of 2 has been added in for the AC, whereas that doesn't appear for the DC. Wouldn't there be a convenient way of, if we were to equivalently represent this in terms of AC in a similar fashion as V RMS square over R, then what should this V RMS be? How should it be related to the VP? In other words, the V RMS square here must be equivalent to VP square upon 2. So we would say that V RMS should be equal to Vp upon root 2. If that were the condition, then the same form of representation is possible. Then once we know that the RMS, the power dissipated by the AC signal, is simply V RMS square upon R, which is having the same form as the DC powers dissipated by the resistor. So it turns out that all the AC signals, unless explicitly mentioned otherwise, by default what is specified as voltage refers to the RMS value, and the peak value is root 2 times the RMS value.